Okay, I figure I can try to explain this limiting reactant stuff and this stoichiometry stuff. A lot of times it can be confusing when we put in the chemical reaction information because it doesn't make sense to us. So let's start off by sort of beginning with the analogy that a chemical reaction is basically like a recipe. And if I had a recipe for apple pie that started with 2 crusts and required 10 apples and made 1 pie, it's sort of like a chemical reaction. 2 crusts plus 10 apples makes 1 pie. So again, I can now ask a bunch of questions. If we have 6 crusts, how many pies can we make? And you can do this one in your head. You say, oh, well, it takes 2 crusts. 6 divided by 2 is 3. That's 3 pies. How many apples do we need? Well, if we were assuming we were going to make the 3 pies that we talked about in the last one, 3 pies, and I need 10 apples per pie. 3 times 10 is 30. If I have 8 crusts and 20 apples, how many pies can I make? I was, have to work that through. So again, when we had crusts, what we really were doing was saying, well, 6 crusts, and I'm using a conversion factor. 1 pie is equal to 2 crusts in this recipe. So it's like a factor of 3 to 2, and I get 3 pies. Now, you could do that in your head, but when it gets harder, it's helpful to use the system of conversion factors. How many apples do we need? If I need the 3 pies, and there's 10 apples per pie, 3 times 10 is 30 apples. Now, it gets a little complicated if I have 3 crusts and 20 apples, because truthfully, only one of those matters. One of them I'm going to have extra left over. So I have to kind of figure it out. But I can't directly compare crusts and apples because they're, we've always said you can't compare apples and oranges. I have to get them into common units. So what we do is we're going to say, how many pies could I make from the 8 crusts? How many pies could I make from the 20 apples? Then I'm talking about comparing pies and pies, and I can make a comparison. So note that if I had 8 crusts, that would be at 2 crusts per pie, that would be 4 pies. If I had 20 apples, at 20 apples per pie, that's only 2 pies. So now I say, oh, I only have enough apples to make 2 pies, but I have enough crust to make 4 pies. So truthfully, the crust is not the helpful information. The one that's going to limit the reaction is the apples because it's going to run out. So I'm going to say that I'm only interested in those 20 apples, and that would tell me I could make 2 pies. So just some vocabulary here. In this analogy, when we talk about how many pies can we make, that's what we would call the theoretical yield. It's like how much of one of the products in the chemical reaction can we make. Theoretical yield is generally in grams, not in moles, but it's the same information. Reminding you that when you say, oh, but it's 10 apples per pie, that per is really you making a ratio and dividing and making a conversion factor in your head. You've done it a long time, and so you know what to do, but that's effectively what you're doing. And when we talk about the 8 crusts and 20 apples, when I'm given the information of 2 different reactions, 2 different reactants, I'm giving quantities of more than one ingredient, that's going to be a limiting reactant problem. And our goal is to find out which one of the ingredients or reactants is the limiting reactant. In this case, we'd say apples was the reactant that limited it. And then I could figure out from that what the theoretical yield is. Let's look at another example where it gets a little uglier. So what is the theoretical yield in grams of reacting 1,000 grams of dough with 1,000 grams of apples? Note here, I didn't tell you how many crusts and how many apples. I told you what the mass was. So I'm going to have to give you some information. A pie crust weighs 320 grams and an apple weighs about 114 grams, and a prepared pie weighs about 2,000 grams. So this is really kind of how we do our standard problems. So first, I'm going to focus on the dough. If I had 1,000 grams of dough and each crust is about 320 grams, that's enough for about 3.13 crusts. So I'm looking at that first calculation. And from 3.13 crusts at 2 crusts per pie, that's enough for 1.56 pies. Yes, I know you can't make a half of a pie, but we're just approaching this as if we would in a chemical reaction. Same thing with the apples. I go and I say, okay, well, what about apples? How many pies can I make from the apples? Well, with 1,000 grams of apples, and each apple is about 114 grams, that's like 8 apples. 8.77 apples, and I need 10 apples per pie. That's only 0.877 pies. So I see now that I have less apples than I do crusts. So I only have enough for 0.877 pies based on the apples. So again, in this case, the apples would run out. The apples would be the limiting reactant, and my theoretical yield would be 0.877 pies. But if I go back and reread the question, it said, what is the theoretical yield in grams? So I'd have to convert that to grams. But I do know a prepared pie weighs 2,000 grams. So I take 0.877 and multiply by 2,000, and I get 1,750 grams of pies. Again, this analogy breaks down a little bit because you can't you either have one pie or two pies, but we get the idea. So just to make sure you understand that when we do this, a lot of times students confuse that I have to be careful when I'm comparing items. I have to compare how many molecules or how many compounds and not how much mass they weigh. When I'm making apple pies, one apple has more mass than one pie crust. So I can't just say, oh, you need 10 pounds of apples and 1 pound of pie crust. The item ratio is not 10 to 1. That would be what the mass ratio is. So in a similar way, when I'm making calcium chloride, which takes 1 calcium atom and 2 chlorine atoms, I can't directly compare mass of calcium and mass of chlorine because calcium atoms weigh more than chlorine atoms. So I can't use 1 gram of calcium and 2 grams of chlorine atoms. I would have to say, okay, well, how many atoms of calcium and how many atoms of chlorine? And that's a 1 to 2 ratio. What this comes down to is that when I'm doing all these ratios and saying, well, there's 1 of these and 2 of these makes 3 of these, I have to be comparing moles of the quantities. I can't be dealing with mass. So my first step is always to get everything into mole units. Okay, so again, once I know the moles of one of the reactants, I can use this stoichiometric ratio, and this is the basis of all of our stuff. So I have how many moles of X I have, and I know that the coefficient ratio of Y to X would get me a conversion factor that would help me figure out, well, how many moles of Y can I make from that? So I'm using the coefficient ratio. We sometimes call that the stoichiometric ratio. So now let's talk through a stoichiometry problem with and without limiting reactant. So the general steps, and this will work for every stoichiometry problem. First, make sure you have good chemical formulas for the reactants and products and have a balanced equation, because if you don't have either the right equation and the right formulas and you don't have the right coefficients, nothing else is going to be right. And then look at what information you're given information about. Generally, you're given how many grams of a reactant you have. And you have to figure out what it is that you're trying to figure out. So what is the desired substance like, in this problem? You're going to convert the quantity of the given substance into moles. So usually that's grams divided by molar mass equals moles. But sometimes the problem gives you moles already. It says if you add 3 moles of oxygen and 2 moles of hydrogen, in that case, you don't need to convert the quantity into moles if it's already given to you in moles, only if it's given to you in some other units. The step 4 is the main step to every stoichiometry problem that will always be present. And that is I'm comparing moles of one reactant to moles of another product using the ratio of the coefficients. And I can use it just like we did with dimensional analysis. If I take the coefficient of what I'm given and put that on the bottom, it's like it's going to cancel out the given chemical, the reactant, and I'll convert it to the desired product chemical. So instead of really changing units, I'm changing what chemical formula I'm talking about. And then finally, converting the moles into whatever the problem is asking for. Sometimes it doesn't care. You can just leave it in moles and say how many moles you make. But if it's asking for mass, for instance, you'll have to convert to mass. Okay, look at the asterisk down at the bottom. This is where it gets complicated. If you are given 2 or more givens, that's a limiting reactant problem. So if you're told 2 grams of oxygen and 3 grams of hydrogen, I have to repeat this process for each one and then pick the smaller answer. The smaller answer will tell me the actual theoretical yield, and the given reactant that got me the smaller answer is considered the limiting reactant. So let's look at an example. In the reaction of aluminum sulfide with water to form aluminum oxide and hydrogen sulfide, A, what is the limiting reactant if 1.50 grams of aluminum sulfite reacts with 1 gram of water? And B, what is the theoretical yield if the same amount reacts? So if I look at the chemical reaction, I'm supplying the balanced chemical reaction for you. And notice I'm putting the quantities directly underneath it, so I'm sort of organizing. I'm seeing that I'm given quantities of 2 different reactants, and so that helps me to see, oh wait, this is a limiting reactant problem because I'm given 2 quantities of 2 reactants. So so the first thing I'm going to do is I'm just going to start from the aluminum sulfide. I'm assuming that there's plenty of water and the aluminum sulfide is the limiting reactant. So I make that assumption and I'll see what I would get as an answer. So I'm going to convert aluminum sulfide into moles. So I'm going to use its molar mass, divide by its molar mass, and I found out I have 0.00999 moles of aluminum sulfide. And then I say, yes, but how many moles of aluminum hydroxide can I make from that? So it's 0.00999 moles of aluminum sulfide times, in this case, there are 2 moles of aluminum hydroxide on the product side for 1 mole on the reactant side. So I'm going to be multiplying by 2 and I get 0.01998 moles of aluminum hydroxide. And my last step is to figure out how much that aluminum hydroxide would weigh. So I multiply by the molar mass, 78.01 of aluminum hydroxide. And I could make 1.56 grams of aluminum hydroxide. Okay, I'm going to repeat the process for water. So in this case now I'm making the assumption that water is the limiting reactant, and I'm going to start from scratch. I calculate the moles of water by dividing the 1 grams by the molar mass of water. I take the number of moles of water and I multiply it by a ratio of 2 to 6 because 2 moles of aluminum oxide are made from 6 moles of water. And then I take that answer and I multiply by the molar mass of aluminum hydroxide to figure out how much that weighs. Note that when I'm done, I'm now comparing 1.56 grams of aluminum hydroxide with 1.44 grams of aluminum hydroxide. Now they're in the same units. They're both masses of aluminum hydroxide. And so from this, I now can say, oh, 1.44 grams is smaller. That means that the assumption that water is the limiting reactant was the correct assumption, and that means that 1.44 grams would be considered my theoretical yield to the reactant. And it also means that the answer that got me that, which was water is the limiting reactant. So this is how we're going to generally approach these limiting reactant problems. They're kind of long and tedious, but if you follow back the steps of stoichiometry, it will always work. And if we see this, we see that the first information, even though we went through all that work, is not really relevant because it's the excess reagent.